Have you ever stopped to think about what connects something like the fizz in your soda, the battery that starts your car, and, well, the very DNA that makes you you? The answer, of course, is chemistry. And today, we're going on a grand tour of the fundamental rules that run our world. We're going to go from really simple mixtures all the way to the complex machinery of life itself.
Now, that question, it's not some trick riddle. It's really a doorway into understanding how things work. See, the answer uncovers these hidden chemical principles that, believe it or not, tie all of those things together. So just, keep it in the back of your mind as we go. I promise, by the end of this, you'll totally see the connection.
All right, so here's our game plan for today. First up, we're going to tackle the basics, how things mix together in solutions. Then we'll see how you can actually get power out of those mixtures. After that, we'll get into the speed of chemical reactions, meet some of the most important metals that literally build our world, and then wrap it all up by seeing how everything comes together to create the molecules of life. Okay, let's dive right in. First up, solutions. This is really the ground floor of chemistry, all about how different things mix and interact with each other. And it's happening everywhere. I mean, think about it. It's in your morning coffee, it's what the oceans are, and it's even happening inside your own bloodstream right now. So let's kick things off with a really powerful idea called Henry's Law. The easiest way to get it is to just picture a can of soda. Why is it so fizzy? Well, it's because they cram a ton of carbon dioxide gas into that can under really high pressure. Henry's Law basically just says this. The more pressure you put on a gas above a liquid, the more of that gas is going to dissolve into the liquid. Simple as that. The moment you pop that tab, you release the pressure, and poof, all that gas comes rushing out. And this law is way more important than just making your drinks fizzy. Remember that scuba diver I mentioned at the beginning? Well, here's the connection. The exact same thing happens to them. When they're deep underwater, the immense pressure forces more nitrogen from the air they're breathing to dissolve into their bloodstream. Now, if they come up to the surface too quickly, that pressure is gone, and the nitrogen bubbles out of their blood, which is incredibly dangerous. They call it the bends. That is literally Henry's Law in painful, real-world action. And that's why, to prevent it, deep-sea divers often breathe a mix with helium in it, because helium doesn't dissolve in blood nearly as easily. You know, in a perfect textbook world, every mixture would be what we call ideal. It would behave exactly like the math says it should. But reality is a lot messier, right? Most solutions are actually non-ideal. And that's all because of how the molecules themselves attract or repel each other. If the different molecules in the mix like each other more or less than they like themselves, well, the whole solution starts acting in weird, unexpected ways. Nature just loves to find balance, and osmosis is a fantastic example of this. Just imagine you have a special screen, a membrane, that only lets water molecules through, okay? Now put salty water on one side and fresh water on the other. What happens? The fresh water will actually start moving through the screen over to the salty side, all on its own, trying to dilute it and even things out. This isn't just a neat trick, it's a fundamental process that's keeping every single cell in your body alive as we speak. But here's where things get really clever. We humans figured out how to hijack this natural process. If you take that salty side and apply a whole bunch of physical pressure, more than the natural osmotic pressure, you can actually reverse the flow. You can literally squeeze pure freshwater molecules out of the salt water, leaving the salt behind. And that, my friends, is reverse osmosis. It's the incredible technology we use to get fresh drinking water from the ocean. All right, so we've got a handle on how things mix. Now let's take it a step further and see what happens when we use those mixtures to generate power. This brings us to the world of electrochemistry. This is the science that's all about the connection between chemical reactions and electricity. It's the magic behind everything from the tiny battery in your remote control to the massive one that starts your car. When it comes to these electrochemical cells, there are pretty much two main flavors. First, you've got electrolytic cells. Think of this like charging your phone. You have to put electricity in to force a chemical reaction to happen. Then you have galvanic cells, or voltaic cells. This is your phone when it's actually running. A chemical reaction is happening on its own inside the battery, and it's producing electricity. So one eats power to make chemistry happen, and the other uses chemistry to make power. So yeah, basically, anytime you're using a battery, what you're really using is a galvanic cell. Let's pop the hood on a few different kinds of batteries and see exactly how they work their magic, turning chemistry into electricity. Let's start with the classic, the one you find everywhere, the disposable battery. This is what we call a primary cell, and primary just means it's a one-and-done deal.
Once the chemicals inside are all used up, that's it, you throw it away. At one end, the zinc casing literally gives away its electrons. Those electrons then have to travel through your flashlight or whatever, creating an electrical current before they get accepted on the other end. It's simple, it's effective, and, well, it's disposable. Now, your car battery is a whole different beast. It's a secondary cell, and that's just the fancy way of saying it's rechargeable. When you turn the key, lead plates inside react with acid to create that massive jolt of electricity needed to start your engine. But then, as you're driving, your car's alternator forces electricity back into the battery. This reverses the whole chemical reaction, basically recharging it and getting it ready for the next time you need it. And this is a peek into the future of power. This is a fuel cell. The best way to think about it is like a battery that never dies, as long as you keep giving it fuel, like hydrogen. What it does is combine that hydrogen with oxygen from the air, and in the process, it generates electricity. And the best part? The only thing that comes out the other end is pure water. It is an unbelievably efficient and clean way to make power. Okay, so let's circle back to that rusting car from the beginning. Believe it or not, rust is just a really, really slow and very unwanted version of a battery. The iron in the car's metal acts like one end of the battery, giving up its electrons to the oxygen in the air. And that process creates iron oxide, which we just call rust. It's the exact same electrochemical principle we've been talking about. It's just, well, this one slowly destroys things instead of powering them. So we figured out what happens in these reactions, but that brings up a new question. Why is a reaction like rust so incredibly slow, taking years, while other reactions are literally explosive? That question is at the heart of our next topic, chemical kinetics. This is the science of how fast reactions go. So if you want to speed a reaction up, how do you do it? Well, there are two really basic ways. First, you can just pack more of the starting chemicals, the reactants, into the same amount of space. You increase the concentration. It's just a numbers game. More molecules bouncing around means they're going to collide more often, and you'll get more reactions. The other way? Just heat it up. When you raise the temperature, you're giving all those molecules more energy. They start zipping around faster, they collide more, and when they do collide, they hit each other a lot harder. I like to think of a reaction as needing to get over a big energy hill before it can get going. That hill, that's the activation energy. Now, what a catalyst does is pretty amazing. It doesn't push the molecules over the hill. Instead, it finds a totally different path, a shortcut with a much, much smaller hill. Because the hill is lower, way more molecules have enough energy to make it over, and the whole reaction just takes off, going dramatically faster. And the catalyst itself, it doesn't even get used up in the process. Now, when chemists are really digging into reaction speeds, they use a couple of key ideas. The first is reaction order. This is the part that's pure experiment. You go in the lab, you double the concentration of one chemical, and you measure how much faster the reaction gets. That's the order. Then there's molecularity. This is more of a theoretical idea. It's our best guess for how many molecules have to smash into each other at the exact same time in a single step for the reaction to happen. They're definitely related, but it's important to remember, one is what you prove in the lab, the other is what you predict on paper. And speaking of catalysts, the things that speed up reactions? Well, a ton of the best ones come from a very specific neighborhood on the periodic table. We're talking about the D-block elements. These are the transition metals, and they are the absolute workhorses of our world. Think iron, copper, titanium, gold, the list goes on. So what's the big deal with these guys? What makes them so special? For one thing, they form these absolutely beautiful colored compounds. But the really crucial part is that they can have variable oxidation states, meaning they can hold different amounts of positive charge. This chemical flexibility is their superpower. It's what makes them so versatile, and it's the exact reason so many of them are such fantastic catalysts. And of course, they're great at mixing with other metals to make super strong alloys, like steel. Okay, here's a weird but really important little quirk of the periodic table. If you look at that series of elements usually tucked away at the bottom, the lanthanoids, something strange happens. As you move from left to right, the atoms actually get smaller. The reason's kind of nerdy, but basically, their inner electrons do a terrible job of shielding the outer electrons from the increasing pull of the nucleus. But here's the big takeaway. Because of this lanthanoid contraction, the heavy transition metals that come after them end up being almost the exact same size as the ones right above them on the table. And that makes their chemistry surprisingly similar.
All right, let's switch gears a bit. We're going to zoom in from looking at single elements to the much more complex world of organic chemistry, the chemistry of carbon. And we'll start with a really common and important group of molecules, haloalkanes and haloarenes. That's just a fancy name for hydrocarbons where at least one hydrogen has been kicked out and replaced with a halogen, like chlorine or fluorine.
The very first thing chemists do with these is classify them. And it's actually pretty simple. You just look at the carbon atom that the halogen is attached to. Is that carbon bonded to only one other carbon? Then it's primary. Is it bonded to two others? It's secondary. And if it's bonded to three, yep, you got it, it's tertiary. And this isn't just for fun. This simple little label tells us a whole lot about how that molecule is going to behave in a reaction.
We can even get a little more specific with our naming. Check this out. If the halogen is on a carbon that's directly next to a carbon-carbon double bond, we give it a special name, an allylic halide. That specific spot right next to the double bond makes that halogen way easier to pop off, which means these molecules tend to be extra reactive. And there's a similar idea here. If that halogen is on a carbon that's stuck directly to one of those stable benzene rings, we call it a benzylic halide. Just like before, being in that unique position gives the molecule a whole set of special properties. It totally changes how it reacts and how fast it does it. Okay, this next part is seriously cool. It's about the 3D shape of these molecules. When they react, that shape can actually change. Sometimes the new piece that's attaching comes in from the back, and it flips the entire molecule inside out, kind of like an umbrella getting caught in a gust of wind. We call that inversion. Other times, it comes in from the front and the shape stays exactly the same. That's retention. And sometimes you get a perfect 50-50 mix of both outcomes, and we call that racemization. And that brings us to our final stop on this tour. We're going to the heart of it all, the chemistry of life itself. This is where all the concepts we've been talking about, solutions, energy, the speed of reactions, all of it comes together to build the magnificent and complex things we call biomolecules. So let's try to build a protein from scratch. Where do we start? Well, everything begins with these relatively small molecules called amino acids. These are the fundamental building blocks, like individual Lego bricks. Our bodies mainly use about 20 different kinds, and each one has its own unique little side piece that makes it different. Okay, so you've got your Lego bricks. The next step is to start linking them together. One amino acid connects to another, and the link they form has a special name, a peptide bond. When you start stringing a whole bunch of them together, you end up with a long, kind of floppy chain called a polypeptide. And that specific sequence of amino acids, that's what we call the protein's primary structure. But here's the thing. A long, floppy chain can't really do much of anything. To actually have a job in the cell, it needs to fold up into a very specific 3D shape. And it does this using hydrogen bonds. These bonds form all along the backbone of the chain, pulling it into these really elegant repeating patterns. You get these coils called alpha helices and these flat folded sections called beta sheets. This level of folding is called secondary structure, and it's the first major step to making a protein that actually works. But wait a minute. How does the cell even know which amino acids to link together and in what order? That's where the master molecules come in, the nucleic acids. You've definitely heard of them. DNA, the famous double helix, is like the permanent master blueprint that stores all of our genetic information. And RNA is its trusty sidekick. It's usually single-stranded, and its job is to act as a messenger, carrying the instructions from the DNA blueprint out to the part of the cell that actually builds the proteins. And there you have it, a whirlwind tour, right? We've seen how the exact same principle that makes your soda fizz is what puts scuba divers in danger of the bends. We've learned that the chemistry that powers a battery is really just a controlled version of the chemistry that makes a car rust. From the simplest mixtures all the way to the genetic code that defines life, these are the fundamental rules our entire universe plays by. But you know, this isn't just a bunch of facts. It's a toolkit. Understanding these rules is exactly how we do amazing things, like designing life-saving drugs, creating new sources of clean energy, and inventing materials that we couldn't have even dreamed of a generation ago. It really gives us the power to solve huge problems and to shape our own future. So I'll leave you with this question. Now that you know the rules, what are you going to build?